This should not be here. Buried inside a corroded lump from a Roman-era shipwreck were dozens of precision bronze gears. Turn one handle, and the machine could model the sky, the sun, the moon, eclipses, calendars, and perhaps the wandering planets. It was built more than 2,000 years ago. Nothing comparably complex survives from the next 1,000 years. So who made it? What exactly did it predict? And why did this technology appear to vanish? The story begins in 1900, off the tiny Greek island of Antikythera. Sponge divers found a wreck loaded with statues, glassware, coins, and ordinary cargo. Among the objects brought to Athens was an ugly green-brown mass. At first, it looked like scrap. Then the crust split. A bronze gear appeared inside. Archaeologists eventually recognized multiple fragments from one device, built around the late 2nd or early 1st century BC, and lost when the ship sank around 70 BC. Saltwater had destroyed the wooden case and transformed much of the bronze into fragile corrosion. Yet the damage preserved clues in layers: gear teeth, shafts, scales, and faint Greek inscriptions. The surviving pieces contain about 30 known gears, but the original machine likely held more. It was compact, roughly the size of a thick book, not a temple-sized observatory. The mystery was now physical. How could so much astronomical machinery fit inside so little space? Researchers could not simply pull the fragments apart. Conservation had to protect information trapped in the corrosion itself. Radiographs revealed hidden wheels, but modern X-ray computed tomography changed the investigation. It let teams see through the crust, count buried teeth, trace gear trains, and recover inscriptions too faint for the naked eye. The object stopped looking like random clockwork. Its ratios formed a mathematical language. A gear ratio is a number made physical. If one wheel has twice as many teeth as another, their rotations remain locked in a precise relationship. The Antikythera builder chained those relationships together to encode cycles in the heavens. A user turned a hand crank to select a date. Pointers and dials then moved to show astronomical results. This was not a device that observed the sky. It computed what the sky should look like from stored mathematical models. One rear spiral represented the Metonic cycle. 19 solar years are nearly equal to 235 lunar months. That relationship helped reconcile a lunar calendar with the seasons. Another dial tracked the 4-year cycle of major Greek games. These were not decorative wheels. Each cell carried information, and a pointer walked through them as the gears advanced. The machine compressed years of calendrical reckoning into a motion of the hand. The lower rear dial went further. It encoded an eclipse cycle, indicating when lunar or solar eclipses were possible, and preserving details about their timing and character. It did not predict weather or fate. It used repeating astronomical periods. To someone who had watched the sun disappear at midday, though, a box that could warn of the next darkening must have felt close to supernatural. The moon posed a harder problem because it does not move at one constant apparent speed. A remarkable pin and slot arrangement caused one gear to speed up and slow down relative to another, reproducing part of the moon's uneven motion. The 2006 Nature study linked this mechanism to the lunar theory associated with Hipparchus. The builder was not merely counting days. The gears embodied a geometrical model of changing celestial motion. The front face is the biggest missing chapter. Surviving inscriptions and mechanical evidence show displays for the sun and moon. They also suggest the 5 planets known to antiquity may have appeared there. In 2021, a University College London team proposed a compact reconstruction that fits those displays into the narrow surviving space. It is an ingenious model, but it is still a reconstruction, not a recovered original. That distinction matters. Scientists agree on many rear dial functions because the gears and inscriptions provide strong physical constraints. The exact architecture of the lost front gearing remains debated. Different teams can satisfy parts of the evidence with different arrangements. A beautiful working replica proves that a design is possible. It does not automatically prove that the ancient maker used that exact design. Could ancient craftspeople really manufacture it? Yes, Hellenistic workshops could cast bronze, cut thin plates, divide circles, engrave scales, and build complex instruments. Ancient writers also described mechanical models of the heavens. The Antikythera mechanism is extraordinary, but it did not fall from another civilization. It sits at the intersection of Greek astronomy, mathematics, metalworking, and generations of accumulated craft knowledge. What we do not have is the workshop, the maker's name, or a shelf of surviving examples. Bronze was valuable and often melted down. Wood decayed. Machines broke. Shipwrecks are unusual time capsules, and this one happened to seal a fragile technology underwater. The apparent thousand-year gap may reveal less about what people could build than about which objects had any chance of reaching us. Calling it the world's oldest known analog computer is useful, as long as we hear the word known. It converted an input, the selected date, through mechanical operations into multiple outputs. But it was not programmable like a modern computer. Its instructions were built into the geometry of its gears. That limitation is also its brilliance. An entire theory of cycles made portable, repeatable, and visible. The Antikythera mechanism did not predict the future. It predicted patterns. Its maker took observations spanning generations and folded them into bronze, one tooth at a time. Then a ship went down, the case disappeared, and history nearly forgot the machine. What survived was enough to overturn a comfortable assumption. Sophisticated technology does not always arrive in a straight line. Sometimes it sinks, waits 2,000 years, and forces us to rewrite the timeline.